Laplacian matrix. Using the Laplacian matrix, we can count. Okay. So that's the point. Now I want to give the proof of this matrix truth here. Okay, or maybe let's quickly go over the corollary. Which one should I do first? Yeah, I will later forget the corollary. So let's just do the corollary first, which was kind of covered in the tutorials, but so this is a very famous theorem of Cayley that the total number of labeled trees with n vertices is n to the power n minus 2. Okay, so how does that come from Kirchhoff's theorem? So the proof is, of course, via, what graph is it that we should consider? It's the complete graph. So this is the proof of the corollary. So the number of labeled trees on n vertices is same as number of spanning trees of the complete graph. So here it's important that we are talking about labeled trees. So what I mean is when n is 3, we wrote down last time there is only one tree structure, really speaking. There is nothing else possible. All trees look like this. But we don't regard it as one because labeling is important. So we could label it as 1, 2, and 3. Or we can label it as 2, 1, and 3. Or you can label it as 3, 1, and 2. There are 3 trees. Now, there is no meaning to labeling this 3, 2, 1. It's the same as this tree because it is, you can see that you can just turn this around and you will get the same. So it's really the number of different adjacency matrices, if you like, we are counting. Okay, so it's not, these 3 are not isomorphic, as I have not generally defined isomorphism, but you can define isomorphism of graphs, depends on how you do it. When we have the vertices are labeled, then the label must go to label. For example, this graph is not isomorphic to this because vertex 1 has degree 1 here, whereas it has degree 2 here. So there is no isomorphism that maps 1 to 1, 2 to 2, and 3 to 3. That's not possible. Okay, so given that, it is clear that number of labeled trees on n vertices is the same as the number of spanning trees of Kn. Right? Okay, just a little thought will show you that that is what is true. So, and this is equal to, so for the complete graph, the Laplacian is what do we have on the diagonals? Every vertex is connected to every other vertex. So the degrees of each vertex is n minus 1. This is an n cross n matrix. Every vertex is connected to every other vertex. So the degrees are n minus 1 and everything else is minus 1. As we saw in that illustration, everything else here is minus 1. All off diagonal entries are minus 1. So which we can write very simply as n times identity matrix minus the constant 1 matrix. J is the matrix, all 1 matrix. This is a rank 1 matrix. Eigenvalues are, so there is one eigenvalue n with multiplicity 1. And all the other eigenvalues are 0. So the multiplicity is n minus 1. Okay, the multiplicity is of the 0 eigenvalue is n minus 1. Therefore, if you subtract from a multiple of identity, so L has eigenvalues are n minus the eigenvalues of j. So n, That's correct. So eigenvalues of L are not what I want. I want eigenvalues of L hat, right? So that is important. So we have to, I forgot. So L hat will be, you just take the top part of it. So which becomes n times identity n minus 1 minus j n minus 1, right? If I just take, if I remove the last row and last column, so let's say remove last row, last column. Then we get this one. Its eigenvalues are n minus the eigenvalues of this. One of them is n minus 1. The rest of them are 0. And how many are there? N minus 2 of them, and this is one of them. So this one is 1. So this is 1, and these are all n. So the determinant being the product of eigenvalues is n raised to the power of n minus 2. So that's exactly what Cayley is saying, that the total number of labeled trees is n to the power n minus 2. Okay, any questions here so far? So if not, let me proceed. So the point is, we need to prove the matrix tree theorem. It's a little surprising, as we discussed last lecture, why the Laplacian matrix should be able to count all these kind of things very nicely. Just taking a certain determinant gives you the number of spanning trees. So how does that happen? Okay, so let's now do that. Okay. Proof of matrix tree theorem. Okay, so we want to prove this, that the number of spanning trees is equal to determinant of L hat, where so we will just here the point is, this question was asked last time, can we drop any row and any column? Yes, we can, but what we will do here is we will just drop the last row and last column. So equivalently, you can drop any row and the same column. What if I drop first row and third column? That is a point I will leave for you to think or put it in the exercises. Okay, so in the lecture, I will just drop the same row and same column, because that has a little more meaning. Although the answers will be given, dropping the same row and same column has a certain meaning graph theoretically, which we will see. Okay, so the main idea is we need a different representation for L, something that I have not said. I think Naneshwar may have mentioned it last time. I forget now. So introduce, so the first step is introduce the vertex edge signed adjacency matrix. I will say what I mean, but it's always, as usual, good to keep an example in mind. So let's have one graph here. Okay, so what is the vertex edge signed adjacency matrix? Adjacency matrix was, we had rows indexed by vertices, columns indexed by vertices, and we would put a 1 if there is an edge between two vertices. Here, what you do is you put the vertices, index the rows by vertices. Let me show you in the example first. So you put the vertices down here and write down all the edges. Okay, so you can write it in any order you like. Just to keep my bookkeeping clear, I will write it in some kind of lexicographic order. 1, 2 is an edge, 1, 3 is an edge, 1, 4 is also an edge. Then 2, 3 is an edge. 2, 4 is an edge. Sorry, 2, 4 is not an edge. 3, 4 is an edge. Okay, so this is 4 vertices, 5 edges are there. And where do I put ones? I put ones at wherever there is if 1 is a part of this edge, then we put a 1. So we put a 1 here. So here it is a 1, 1, 0, 0. Now 2 is in which of these edges? Yes, this edge, 0, 0, yes, 1 and 0. And if we do this 3, then we will get it's 0 here. 3 is not part of this edge. 3 is a part of this edge. So 1, it's part of, not part of this edge, part of this edge, part of this edge. For 4, it is 0, 0, 1, 0, 1. Okay, so this matrix is called a, so if you look at this matrix, this is a 4 by 5 matrix. So 4 is the size of the vertex set, 5 is the size of the edge set. Okay, 5 is the number of edges, 4 is the number of vertices. So this is called a vertex edge adjacency matrix. But what I want is a signed version of it. Okay, so what is a signed version of it? So what we do is, so let's label the vertices. We can do it in many ways, but here is a simple rule. In each edge, there are 2 vertices, right? So on the smaller one, put a minus, not a plus. Don't put 1 everywhere. Some of them I will make a negative. And which one I will make negative? I need some consistent rule. And my rule is that the smaller vertex will get a minus. Okay, so 1, 2, 1 is the smaller one. So I put a minus here. 1, 3, 1 is a smaller one. I put a minus. 1, 4, 1 is the smaller one. I put a minus. 2, 3, 2 is the smaller one. So that will get a minus. 3, 4, 3 is the smaller one. That will get a minus. Okay, so this is the signed vertex edge adjacency matrix. So now let me define it in abstract, in general. So B, this is a matrix. So this is, B is a V cross E matrix. Okay. So for convenience, let us, so the rows are rows indexed by V, which is I am taking to be 1, 2 up to n, and columns indexed by E, which is there may be any number of edges, which I will call E1, E2, Em. Then this will be an n cross m matrix, and the I comma k entry is +1 or -1 or 0. There are 3 possibilities. So if so, it is 0 if I is not part of Ek. Okay, if Ek is some edge, and okay, so let us maybe let me write. So the kth edge, let Ek is an edge. So let us say it is an edge between some 2 vertices, which I will call U and V, with U less than V. Okay, so Ek, the kth edge is having 2 vertices. Let's say U and V, and U is smaller than V. So you put a 0 if you put a 1 if I is equal to V. You put a -1 if I is equal to U, and you otherwise you put 0. That's what I did here. Okay, so I hope this is clear what the vertex edge signed adjacency matrix is. Is okay. Is any questions about this definition? Okay, if not, now what is the relevance of this? What is the relevance of this to the Laplacian? Anyone?
Laplacian equals to B into B transpose.
Okay, very good. So that is the point. So then the main point for us is that then L is B times B transpose. Okay, B has V cross E and B transpose will be E cross V. So B transpose will be V cross V matrix. So this is this. Now, why is that true? Well, let's first see the diagonal entries. What do you get on the diagonal entries? When you do B times B transpose, let's just do it in this example. I think the general case will be clear. So this is B transpose. Let me just write a couple of -1, -1, 0, 0. Let me write the second column will be 1, 0, 0, -1, 0, and so on. So when I do B times B transpose, say if I want a 1, 1 entry, what will I get? I'll get the first row times first column here, but that will be just the norm squared of the first row, right? You will get -1 into -1, -1 into -1, -1. So BB transpose 1, 1 entry will be the number of ones here. So namely the degree, the 3, which is how many vertices. So BB trans. So the 1, 1 entry of BB transpose will be exactly how many edges is 1 a part of, which is exactly the degree of 1. And that's what on L11, right? L11 is supposed to be the degree of the vertex 1. What about the 1, 2 entry? If I multiply 1 by 2, what happens? So this times this, and this times this, and so on. So what happens is that you see that the BB transpose, when will it get it will either get a -1 or a 0. When will it get a -1? If there is, you see, in this case, there is some column in which this has a -1 and this has a 1, or vice versa. So that's why we get a -1. If we were to do 2 and 4, for example, the 2 inner, it's basically BB transpose. Okay, one way to think is BB transpose. If you want to look at the IJ entry, it is the inner product of ith row of B with jth row of B. Okay, what do you get when you take inner product of ith row and jth row? You may get 0 or -1. You see, for example, 2 and 4, if you take the inner product, there is nothing common. Where there are ones here, there are zeros in the other, so you'll get a 0, and there is no edge. But if there was an edge in which they were common, like 1 and 2, then you will have a column in which they both of them have a non-zero entry, and there can be only one column. Okay, because each edge can connect only 2 vertices, there can be only one row, one column common. So if you look at 1 and 3, then they have this fourth row, there is a -1 and 1, but everywhere else we get 0. Product will give me 0. So when you take inner product, you will get -1. 1 and 4 similarly, here you will get a -1, 1 and -1, but all the other things are 0. So L is BB transpose. So if this is not clear, I will say I have already indicated, but if you want, if it's not clear, go back and think about it, and it is true. L is BB transpose. Okay, so this is incidentally another proof why L is positive semi-definite. You have expressed L as BB transpose. That is a way to check positive definiteness. Okay, any questions so far? Is it clear? Okay, I hope so. If not, please at any time, please unmute yourself, ask questions, interrupt me. If you want me to repeat something, I'll be happy to, etc. Okay, so how is this helpful? That is the second question. So step 2. So let's make one.
Excuse me.
Yes.
Can you please explain why the off-diagonal entry is -1? Well, I can see the calculation coming out to be -1, but can you explain, like, in general, why is it happening? Like
so you see the ith row. Okay, so the ith row will have what? Suppose E1, E2, EM are the edges. Okay, so you will have either +1 or -1, right? Or zeros, etc. Now jth row will also have suppose they have one has a +1, each row, each column is, there can be 1 minus 1 and 1 plus 1. You see that, right? So in each column of B, there is exactly 1 plus 1 and 1 minus 1 and the rest are zeros. So if ith row and jth row have this common thing, so one of them must be -1, one of them must be +1. Okay, and that means that I comma j form the edge E2, right? I and j form the edge E2. If this is common, then there can be no common thing in other words. All the other edges are different. One of them must have a 0. In every other edge, there is only one edge connecting I and j, at most one edge. If there is no edge connecting I and j, then I and j are not adjacent to the same edge ever. So all the corresponding things, if there is a 1 here, there will be a 0 here. If there is a -1 here, there will be a 0 here. But if they do share an edge, that can happen in only one edge, namely the edge I comma j, and then one of them has to be +1 and one of them has to be -1.
Okay, okay, got it.
Is it okay?
Yeah, thank you.
Okay, so that is the reason why you get -1s. Okay. So one of the observations that I will make, maybe we will prove it later, is, so a claim, this is important for later purposes, that you take any submatrix, any square submatrix, of B has determinant equal to 0 or 1 or -1. Okay, all the determinants are actually 0 or ±1. Okay, in fact, it may be 0 or 1. Is it true? If I take it in that order, I think it will be 0 or 1. So for example, just look at this one. Okay, if you take any one entry, so let's take, for example, so just to illustrate here, suppose you take the first two rows and this one. This is a square submatrix, right? I take first and third row, first and second column. So then I get this 2 by 2 matrix, -1, -1, 1, 0, 1. What is the determinant of that? -1 into 1 is -1, right? Okay, in this case, you do get -1. So it is -1. Suppose I do some other, I take some other thing. So suppose I take second and third row, and let us say we take second and fourth column, for second and fourth row and second and third column. Now this is 0, 0, 0, 1. If you take determinant, you get 0. So so it is true. Okay, so the claim is that it's not just for 2 by 2, but you take any 3 by 3. So you take any 3, for example, we can take these 3 rows and maybe this column. So then I'll get a 3 by 3 matrix like this. Okay, -1, -1, 0, 0, 0, 0, 0, 1, -1. You calculate the determinant of it, you will get what is, in fact, it is probably easy to do because the last column is 0, 0, 1. It will be 1 times the determinant of this, and that will be, I think, -1 or 1. Okay, so
is 0.
Is it 0? Oh, sorry, you are right. You are right. It is 0 because you expand by the last column. So the matrix I'm talking about is now, the matrix here is -1, -1, 0, 0, 0. Oh, okay, there is a 0 row. So it will be, determinant is 0. You're right. The determinant is 0. So all determinants will be 0 or 1 or -1. Okay, so this is something that will be useful to us. But I postpone the claim to the tutorial, or maybe I will do it after the class. So I hope by examples you are at least willing to accept this fact. Sometimes this type of lemmas, you should not read the proof directly. When you're reading math, first of all, what is even the use of this? This doesn't seem relevant to whatever we are doing, so you should postpone it. So what is the point of it? We should understand first. Then you have sufficient motivation to read the proof of it or find one. Step 2. Here, I may be introducing something that you do not know. If you do not know, then this is an excellent opportunity to learn this very interesting and important fact. So, okay, so L is B transpose, we saw. So let's write it out. So B is like this. So B we should think of as, usually there are more edges than vertices, right? Usually. So I'll write it like this. So it is indexed by edges. Rows are indexed by vertices and columns are indexed by edges. Yeah, so think of this as a long rectangular matrix. So B transpose will be the other way. So B transpose will look like this one. So here of course, the rows of B will correspond to the edges and the columns will correspond to vertices. Okay, so that's how things are. Now, what will be, suppose we remove, so let's, as I said in the proof, we need L hat, right? So delete last row and last column and to get L hat. Okay, so for me, L hat will be got by deleting last row and last column. So can we write it as XX transpose for some matrix? So how do I delete? In terms of L is B transpose. If I delete last row, last column of L, can you write it as X times X transpose for some matrix X?
So we can delete the last row.
You delete the last
row.
Okay, very good. So what we do is we just you just delete the last row here. Okay. So if you just delete the last row of B and correspondingly the last, so corresponding to the vertex N. Okay. So if we delete that, then what remains is this part, right? So what remains is this part.
So figuratively, this corresponds to isolating the last row, right? In a row.
Sort of, but you are deleting the last row, but one should be a little careful. It's not like in the graph you delete the vertex N. You delete the vertex N, but you do keep all the edges, so to speak.
Hello.
Okay. So what I want to say is that let this matrix be C. Okay, so let me put it. Let.
Sudhak marriage fix
question.
Okay.
So let C be the matrix got by deleting the last row of B. Then I am claiming that this particular L hat is just C transpose. Right, because what are the last, what is the last row of L? It is got by taking this row and multiplying each of these things, right? So, but if I delete the last row here, then I end up deleting the last row of L. And how do I get the last column of L? Well, you have to multiply each of the rows by the last column of B transpose. And if I delete the last column of B transpose, then I end up deleting the last column of L. So L hat will be CC transpose, where C is the matrix got by this matrix is C. Okay. So it's saying here that my internet connection is unstable. So are people able to hear me? Am I
Yeah, you're
audible?
audible. Yeah, you're audible.
Yes, sir.
Okay, that may not be audible. Who knows? Oh, okay, fine. Thanks. Okay, so is this any questions about this? So not only is L BB transpose, but we also have a representation for L hat, which we need. Okay, so now how do I calculate the, so C is this matrix. So what does C look like? So if we write down C, it will look like this. It will have one row less. One, two up to n minus one. Now, what is the determinant of, so here I bring an important fact. So the claim, so I will write down and then ask if you know this. So I say that determinant of L hat. So we are taking C and multiplying by C hat. Sorry, C transpose, which looks like this. This is C transpose, indexed by 1 to up to n minus 1 here and E1 up to EM here. So how do I calculate the determinant of one rectangular? See, this is a rectangular matrix, this is a rectangular matrix, but the product is a square matrix. So how do I calculate its determinant? So for example, if it's square matrix by square matrix, then the determinant of the product is product of determinants. But that does not make sense here, right? Because the determinant, you can't write determinant C times determinant C transpose, because C is not a square matrix. There is no determinant. Do you know anything that can be written here? So generalizing that fact, so let me write, it may or may not be something familiar. So let me write here, it is determinant of CS squared. Okay, I will explain what these things are. The sum is over all S, which are subsets of the edges, 1, 2 up to M. And what is CS? CS, so over subsets of size n minus 1. Okay, CS is the matrix got by taking, so if S is a subset of 1 to M of size n minus 1. So let us say S is K1 up to Kn minus 1. Then CS is the matrix got by taking the columns
No.
hello, sorry, I was muted also. I was kicked out of the meeting because the internet connection was unstable. Rajesh, you will have to allow me to share screen again. I have been disabled now.
Okay.
Hello, is Rajesh?
Yes, yes, I am doing.
Okay.
Yes, now you are co-host again.
Okay, fine. Thank you. Yeah, so this may happen again. I don't know what is going on, but all right. So let us go to this. So right. So what I was saying was L hat you write as this rectangular matrix times this rectangular matrix. It's a square matrix. Then the determinant of L hat can be written as the sum of squares of these square determinants. Okay. And what are the square determinants? So what you do is you want a square matrix from here. So what you do is you can take any n-1 columns. Okay, if I take any n-1 columns and all the rows, I will get a square k2 kn-1. Then you take columns and put that together as a square matrix. That matrix we call CS. And you have to do it for all possible subsets. And then take the sum of squares of the
So your voice is breaking a lot. We could not hear.
Can you hear me and can you see the screen now?
Yes, sir.
Yes, sir.
Okay. Sorry, again and again
Yes,
it's
sir.
getting. So I was saying this, that the determinant of this is the sum of squares of these square determinants. And these determinants are got by taking any n-1 columns here and forming a square submatrix. Okay, and then take the determinant and take sum of squares. So have you seen this formula before? Is there
Yes, sir.
anyone? Yeah, what is it called?
Cauchy-Binet formula.
Cauchy-Binet. Is it familiar to everyone? How many of you know the Cauchy-Binet formula? If I may ask, can you raise hands? If you
Yes,
know
sir.
if you know the Cauchy-Binet formula, can you please raise hands in the... Okay, some of you know it. Okay, so some, but only a few it looks like. So maybe it can be a kind of topic for the tutorial or something if time permits. Okay, only 4 people said they know. So this is by the Cauchy determinant formula. Okay, so sorry, the Cauchy-Binet formula. This is called the... It is a very useful one. It's very useful. And so we will assume this. Okay, so it is either something that will be left for you to look up, or maybe it can be covered in tutorials. We'll see that. But this is important because now we can talk about it. So now what happens? So each of this CS is a submatrix of B, right? CS is a submatrix of B. So every square submatrix of B has determinant 0 or 1. So each of these, by the claim above, determinant of CS is 0 or 1 or -1, right? Because it's a square submatrix of B. Okay, so once that is true, so implies determinant square is 0 or 1. When we square it, it will be only 2 possibilities, 0 or 1. So what we will want to prove now is that we now show that this is precisely 1 is either 1 or 0, and 1 if edges of S. What is S? S is a subset of columns, right? So what I mean is edges given by S means you are selecting a collection of columns, right? So those are corresponding to edges. So edges specified by S. Okay, when I say edges of S, I mean edges specified by S. So let S be K1 up to Kn minus 1. So if edges EK1 up to EKN minus 1 form a spanning tree. And 0 if not. Okay, if those edges form a spanning tree, you get 1. If they don't form, then they give 0. Then you see the theorem follows from here, right? Then it follows that this determinant of L hat is precisely the number of spanning trees. See, spanning tree means you have to take a collection of n minus 1 edges such that they form a tree and span all the vertices. I am saying that that's when this will give you a 1, all others will give 0. So determinant L hat is exactly the number of spanning trees of the graph you started with. Okay, so the key thing is to prove this. So any questions? Is it are you following? I mean, so
Here in
if
this
there are
step,
any,
yeah, here in this step, you're trying to say that determinant of CS is either 1 or 0. It can never be minus 1, or
oh,
you're talking about the square.
Yeah, no, square.
It should be square, right?
Yeah. So
Okay.
I should say determinant CS square is 1 or 0. So determinant CS will be minus 1 or 1 corresponding. Yeah, thanks. That's the square, that is 1. Yeah, that would have been a problem if we didn't have square. Then if some are minus 1, some are plus 1, we might get cancellation. That would be bad. That would not help in counting. But luckily we have squares. Okay, so how do we prove star? So one part is easy. So proof of star. So let's see. Suppose EK1, EKM does so EKN minus 1 does not form a spanning tree. Then what do you say? The determinant must be 0. Why is that? So let's go to this example that I had written. So let's take here. So suppose we take the edges. Suppose I take the edges. How many edges am I supposed to take? There are 4 vertices, so I'm supposed to take 3 edges. Suppose I take the edges 1, 2, 2, 3, and 1, 3. Okay, what does that correspond to here, right? 1, 2, 1, 3, and 2, 3. So if I take these 3, and we have removed the last row and last column also. Okay, so what will that give me? So let me use a different highlighter. So that will give me this much, right? So I'm taking and this square submatrix. Is its determinant equal to 0? See, it should be 0, right? 1, 2, 1, 3, 2, 3 do not form a spanning tree. So, but do you see that its determinant is 0?
Yes, sir.
Why?
The sum of rows or columns is 0.
Exactly. The sum of rows or columns is 0. Okay, so that's the idea. So suppose EK1 up to EKN does not form a spanning tree, then there is a cycle. say ek1, ek2, let's say some ekp is a cycle. So this one may be I1, I2. This may be I2, I3, and so on up to the, in the end we get IKP and I1. So that's how we get a cycle. Okay, so this is I1, I2, I3, and so on. IP, IK1 I should have, yeah, IP. Sorry, I should have written IP, I1. Okay, so what is the problem then? Then you see the thing is
Can you
this.
explain why this? Sir,
If it's,
can you explain why this forms a cycle?
no, if it is not a spanning tree, should it form a cycle? I mean, so what does it mean to be not a spanning tree? So you take a bunch of edges and suppose it's not a spanning tree. That can be violated in two ways actually. Okay, it's a good, it could be because it's disconnected, or it could be because it forms a cycle.
It could be disconnected.
Yeah,
Yeah,
but you
Could be
see
also
that
disconnected.
exactly. So, but we have taken n-1 edges. Okay, by the way, if it is n-1 edges, then if it is spanning at all, either it's not spanning, or if it always has to form a cycle. See, you have taken n vertices and n-1 edges. Okay, so this is it is a good point you're asking. I kind of skimmed over it because yeah, okay. So this is something to slightly think about. It's not a complicated point, but we have taken n-1 edges, so there has to be a cycle if it's not a spanning tree. There is no other way. Okay, so that is why there is a cycle. So once there is a cycle, you see the corresponding columns will add up to 0, because none of these edges are using the last vertex. So the point is C misses the last vertex n, but none of these, all these ik, ip are all less than equal to n-1, because these things, these are well, yeah, what am I trying to say? Yeah, they form a cycle.
So there can be isolated vertex also.
Yeah, but then there has to be a cycle somewhere else. You see, the problem is that if you take, so suppose you take a spanning tree like this. So you take this, but you are supposed to take 3 edges now. If you make an isolated vertex somewhere else, there has to be a cycle. So do you agree that if you have a connected graph which has n edges, suppose you have a connected graph with 10 vertices and at least 10 edges, then there has to be a cycle. Do you agree to that?
Yes, sir.
So if you have a connected graph with x number of vertices and at least x number of edges, then there has to be a cycle in that. Now, even if you have isolated nodes and other disconnected components, since you are only having n-1 edges, you see that if you have an isolated node, then among the remaining n-1 vertices, you must have n-1 edges. So if it is connected, you must have a cycle there. And so on. So somewhere there has to be a cycle.
Hello? Hello, sir.
Yes.
Sir, in the last, in the one which you are erasing now.
Oh, okay. Sorry.
Can you please draw it again? Yeah.
Oh, okay, okay.
Here, if you take 3 edges, you said it will be a cycle. Am I right?
Well, either it will be a, no, I say that if it's not a spanning tree, there has to be a cycle. Yeah.
So here, if we are taking for 4 vertices, we are supposed to take 3 edges. Am I right?
Yes.
Okay. Oh, fine. Yes.
You agree?
Yeah. I do.
Yeah. So the thing is, it need not be, yeah. So spanning, yeah. So that's the point to be convinced of, that you will form a cycle somewhere. And once you form a cycle somewhere, those corresponding columns will add up to, so you see those corresponding cycles will add up to 0. So if I get this part, whatever I said, this is not important. This is not the thing. See, the thing is, let's say in I1, I2. So what happens is that so let's for simplicity say I1 is smaller than I2. So then in one column, this will have a minus, in the other, it will have a plus, and so on. So those columns add up to 0. Therefore, the determinant is 0. Okay. So, but if ek1 up to ek n minus 1 does form a spanning tree, the claim is that determinant CS is plus or minus 1. Okay, this actually requires, I mean, I'll probably skip the details because, I mean, it's not that, it is something that one has to convince oneself of. Yeah, so let us see example again. So if you take an example like this, so what is a spanning tree, for example? So let's take a different one. So let's take a spanning tree. 1, 2, 1, 3, and 3, 4. That does give a spanning tree, right? So if I take 1, 2, this does give a spanning tree. So the corresponding matrix is 1, 2, 1, 3, and 3, 4, right? So it is minus 1, 1, 0, minus 1, 0, 1, and lastly 0, 0, minus 1. So what is this determinant? If we expand by the last column, you'll get minus 1 times the determinant of this. So you'll get minus of determinant minus 1, 1, 0. And that is minus 1 into 0, minus 1. So it is overall minus 1. You see, that determinant is actually minus 1. Now, so what we have to convince ourselves is that if it does form a spanning tree, then the determinant has to be plus or minus 1. Okay. In other words, you just need to rule out the possibility that determinant CS is 0. Okay, you need to rule out the possibility that the determinant CS is 0, which is, that is, rule out the possibility that CS is singular. So you have to show that there can't be a linear relationship of columns or of rows, whichever one of them. Okay. So you have to show that there can't be a linear relationship between the columns, for example. So maybe I will, because I will try myself into not writing it out, maybe I will leave this for a moment as sort of to think about. I will maybe write it and post it. Okay, so you can think about it, and I'll just write it and post it. So as to, since I only have half an hour, I want to say a couple of other things. So let me skip that detail and ask you to think about it. And if not, just read whatever I post. Incidentally, I did not give references, so that I should have done. So let me give some references. But other than this checking, are there any questions about this? But once you do this, you see that this point is, these things are exactly counting spanning trees. Determinant CS squared will give you exactly 0 or 1 depending on spanning tree or not spanning tree. Okay, so last class, some of you were asking me for intuition. I don't have a simple intuition, but there is this technical intuition that somehow the spanning tree is condition can be transferred to linear independence of certain vectors. That's what is happening here. So the S forming a spanning tree is equivalent to corresponding columns forming a linearly independent set. And somehow the determinant is also 0 or 1. That's helpful. Okay. Any questions here? Okay, if not, let me leave it, because this is a kind of detail that can be left to either tutorial or I'll write it up in notes. But what I was reminded of was that I did not give any reference books. So maybe I now do that. So in general, references. So one is, there is a nice book by, it is online, available online, by Spielman, called Spectral Graph Theory. These are, this is not yet a book, these are lecture notes. It is available online. So he is in Yale, Dan Spielman is in Yale, he is a computer scientist. So the Spectral Graph Theory book is a nice one. So these topics are all available there, including the one I'm going to do next. Another one, which is a very nicely written book, easy to read, is by Professor Bapat, who you saw last week or maybe earlier last week, right? Bapat gave some lectures. So he has a book called Graphs and Matrices. So this is available in the Trim series. Those red books. So that's also something that is easy to read, and these things are written. Many more things are there in that book. So these are some references. Okay. So let me say one more thing, an extended matrix tree theorem. So I wanted to say a couple of things. Extended. So what is the extended matrix tree theorem? It is like this. So again, we have G is V comma E and L is the Laplacian matrix. So previously we deleted one row, one column, right? So suppose now let L hat, let me call it L tilde, be the matrix got by deleting rows and columns corresponding to some particular vertices, let's say U1 up to U. Okay. Suppose I take the L matrix, but now I just don't delete one row, one column. I take, let's say last three vertices and last three rows, last three columns. Okay. So you delete the same rows and same columns here. So you delete the last three rows and last three columns. So these U1, U2, U3 are the last three vertices there. So what is its determinant? That also has a counting interpretation, and that is this extended matrix tree theorem. What does determinant L tilde count? Okay, then this is the extended matrix tree theorem. This is also the number. What is it a number of? If it was only one, when k is 1, you get back the number of spanning trees. When k is 2 or more, you get something more, something different. So it is the number of spanning forests of G with exactly k trees and such that each of ui is in a different. Okay. First of all, as I said last time, I mentioned it, forest is a collection of trees. So what I mean by that is, so for example, so let's go back to this graph. So let's write this graph again. Where was that example that I was writing? So let's take this 1, 2, 3, 4. Okay, so let's take that particular example. Okay, so now let us say we delete 3 and 2. Okay, so L, what is L? First of all, let's write back L. L is here 3. For 2 it is 2, and for 3 it is again 3. For 4 it is 2, and then 1 and 2 are connected, 1 and 3 are connected, 1 and 4 are connected, 2 and 3 are connected, 2 and 4 are not connected, 3 and 4 are connected. Okay. So suppose you take u1 is 2, u2 is 3. That means we are going to delete this one, this one. So we get L hat. We have to delete second row, third row, second and third row, second and third column. So L hat will give me 3 minus 1 minus 1, 2. And its determinant will be, sorry, not L hat, it is L tilde, what I am calling L tilde. Determinant of that matrix is 3 into 6 minus 1, which is 5. Okay. So what is this counting? Okay, so here I'm saying it is counting something, number of spanning forests with exactly 2 trees, and such that each of these UI is in a different tree. So let's me write an example. So what I want is not a single tree, but 2 trees. Okay, so all the vertices have to be covered, but there have to be 2 trees. And one tree should have 2, the vertex 2, other tree should have the vertex 3. So for example, 2 can be alone. 2 can be alone, and 3, or 2 and 1, and 3 and 4. Okay, so this is a forest. Okay, there are 2 trees. One of them contains 2, one of them contains 3. And that's exactly one of the possibilities. What are the other possibilities? Well, 2 can be alone and all the others are in with 3. So this is a possibility. 2, 1. So this is one other possibility. Okay, any other forest you can think of?
3 alone.
3 alone. Okay, so if 3 is alone, then 2 has to be connected to 1 and 1 has to be connected to 4. This is a possibility. What other possibilities there? 3 and 1
2,
can be
4, 1, 3.
Sorry, say again. Oh, sorry. Yeah, what are the
2, 4, 3, 1.
Can you say that again? 2?
Yes, sir. 2 is connected to 4, 3 is connected to 1.
No, but 2 cannot be connected to 4, right? 2 and 4 are not connected.
Oh, I'm sorry. Yeah.
Yeah, so that is not possible. Yeah, what are the other
2
ones?
is connected to 3 and 1 is connected to 4.
No, 2 and 3 should not be in the same component. 2 and 3 should not be in the same component. So one, but this itself, the following is possible.
Sir, 1, 2, 2, 1, 4 and 3 is isolated. That is done. Okay.
3 is well, 3 is isolated, 2, 1, 4 is, yeah. So this is the only possible. If 3 is isolated, this is the only possible. But when 2 is isolated, this is not the only possible. We can also have 1, 4, and 3. See, when 2 is isolated, we are left with a 3 cycle. I can delete any of those 3 edges.
Sir, can we also have other vertices to be isolated?
No, no, no. Everything has to be spanning. It has to be spanning exactly 2
Okay.
trees. These are all the possibilities. If you see, what I forgot here was when 2 is isolated, this is not the only possibility. These 2 are also possible. Once you isolate 2, 1, 3, and 4 form a triangle. And to get a tree out of it, I can delete any of the 3 edges. So that's how I get 3 of them. So you see, you get 5. And that is this 5. So this is the extended matrix tree theorem, which counts something else. It counts the number of spanning forests with exactly k trees such that each of the specified vertices is in a different component tree. Okay. So I'm not going to prove it. Once you understand the proof of this, and I owe you a little bit of explanation here, which I will postpone in the interest of covering other things. So maybe I will, so then you can think about whether you can prove this also. More or less, you can try to follow the same type of proof, except that instead of this C, you have even smaller. You have deleted even more number of rows. And then you have to think what happens in such a situation. So the proof is there in Bappert's book. Professor Bappert's book has that. Okay. So there are many interesting things like this. So before leaving this topic, let me mention other interesting. So there are other interesting, one can go along these lines. So let G be, so let's take G to be VE, and let's say, so suppose you want to, so let's say you have, again, let me just write that same graph, just 1, 2. Okay. Suppose we have some counting, we can ask further counting questions. How many trees that contain the edge 1, 2? Okay. Or I can ask how many spanning trees that do not contain the edge 1 to 2. I can ask that question. Or I can ask how many spanning trees that contain 1, 2 and also 3, 4. Okay, how many spanning trees are there? So in this specific example, you can work out, right? You can work it out. But how can we solve such problems? So this is very closely related to probability, by the way. These questions are related to probability. Well, in this setting, probability is just weighted counting. Okay, so what is probability? So in other words, of all the spanning trees, if I pick one at random, what is the chance that it will contain the edge 1 to 2? You can ask that question. Well, that is just the number of spanning trees that contain the edge 1 to 2 divided by the total number of spanning trees. For the total number of spanning trees, we have a kind of formula, namely determinant of L hat. But what is the formula for this? Okay. So let me, so all 1, 2, and 3, 4, or 1, 2, 2, 3, etc. We can ask all sorts of questions that contain some particular edges, E1, E2, Ek. Okay, so all such questions, one can think of it as combinatorial questions or probability question. They are the same thing. But what we have is, we know the denominator, we know the total number of spanning trees, but can we count the number of spanning trees which contain the edge 1, 2? Any ideas about this? So let's just do that one simple example. So fix a graph G, E, and fix an edge E. So we want number of spanning trees. So let's say without loss of generality, it is the edge 1 and 2, vertex 1 and 2 are that, let's say that is the number of spanning trees that contain E. Can we have a formula for that similar to the formula for the total number of spanning trees? The thing is, yes, if you think about it, what are the, let's look at this example. If I force that edge has to be there in my spanning tree, then what happens? So if you force that edge to be there, more or less that becomes the same vertex, right? So now you think of this reduced graph where I merge 1 and 2. So what happens if I merge 1 and 2? I make them into a single vertex by just merging it. So that becomes this mega vertex. Now that is connected to 3 like this and like this. So it becomes a multi-graph, okay? You have multiple edges now, but modulo that, this is that merged vertex and this is 3, this is 4. This is the new vertex. See, if you have a spanning tree here which contains 1, 2, for example, that could be 1, 2, and tell me, so let's think of a spanning tree, which it could be 1, 2, 1, 4, and 1, and let's say 2, 3. Okay. So after merging, what happens? What happened to 1, 4? 1, 4 is this edge. And what is 2, 3 is this edge, right? So what you see is that after this merging, it is just a spanning tree of the new graph. You see that, right? You see it is the spanning tree of the new graph. Except you have to be slightly careful that you need to take into account this multiple edges. So you have to go to the weighted situation. Okay, because there are 2 spanning trees. So for example, if you look at the spanning tree, and here, suppose I were to take the spanning tree which contains 1, 2 and 1, 3 and 1, 4. Okay, so one, 2, 1, 3, and 2. 1, 2 is supposed to be there. So I mark that in black. If I do this merging, what happens to that? When I merge this, what I get is again, so I again have this graph with this merged vertex, the new vertex, and 3 is here and 4 is here. And what happens to the spanning tree? Yes, that 1, 4 goes to this edge, right? That 1, 4 goes to this edge. And 1, 3 becomes this edge. So it's again a spanning tree of this graph, but this spanning tree should be thought of as different from this spanning tree. If I have to count, this is different from this. So this has to be counted different from this. So you should keep the multiple edges. In other words, you should give a weight of 2 to that particular. If you call this vertex as 1, now you have a new graph with vertices 1, 3, and 4. And 1 to 3 has a weight of 2, 1 to 4 has a weight of 1, 3 to 4 has a weight of 1. So you have to go to the weighted graph case. So which is why it is useful to study weighted graphs. This is also a motivation why you want to study weighted graphs. But essential idea is that the number of spanning trees that contain the edge 1, 2 is the same as the number of spanning trees in the new graph, which is got by merging the vertices 1 and 2. Okay. So, and for which we have a formula. Okay, so equals, so is exactly equal to the number of spanning trees in the new graph G dash got by merging 1 and 2. Whichever the two endpoints of the edges, you merge them. Except that this is a possibly multiple edge graph. Okay, that's possible. And for that, you have the thing is, it does go through, the Kirchhoff's theorem is also true for weighted graphs. And here you have a formula in terms of L dash hat, okay, where L dash is the Laplacian of G hat. Of G dash, sorry, L dash is the Laplacian of G dash, and you have to delete one row, one column. So this way, you get, for the number of spanning trees which contain 1 to 2, you get a determinant formula also. So on so forth, for all these things, one can get formulas in terms of some determinants, which may or may not be easy to calculate, but one can do it. Okay.
Sir, can you explain the weights once, like which weight is 2, you said?
Because so this new graph, if I want to think of it as a graph, you either write it like this with 2 edges, which is same as a graph with 3 vertices, which I call new 4 and 3. Okay. And this one has a weight of 2 because there are 2 edges between this. This has a weight of 1, this has a weight of 1.
Acha.
Okay. So the corresponding Laplacian, if you ask.
Because 1, 3 and 2, 3, 2 edges from 1, 3 and 2, 3, therefore 2 is the weight.
Exactly. So you have 2 edges here, so you put 2 as the weight. So what will be the Laplacian matrix? You have to take the weights into account. For the new vertex, for 3, the degree is, for new vertex, the degree is the sum of weights, 2 plus 1, 3. For 3, the weight is 2 plus 1, 3. For 4, the weight is 1 plus 1, 2. And then you have to put negative. If between new and 3, you have to put minus 2, minus this. Between new and 4, you have to put minus 1. Between 3 and 4, you have to put minus 1. Like this. This will be the new Laplacian. For the weighted graph, that's how you do the Laplacian. On the off diagonal, you put the negatives of the weights of the edges. On the diagonal, you put the degree, which is the total sum of weights. Again, the row sum and column sum should be 0. Okay, that's the idea. I have made a mistake, I think. No, it is okay. It is fine. Row and column sums are 0.
You accidentally, I think you mentioned something like a quotient when you are merging the 2 edges, like it is quotienting a part of the graph when the merging is happening.
Yeah, I didn't use the word quotienting, but if you want, you can do that. Yes, you can do that.
Yes, so I mean, I was thinking about the quotient in the algebra sense. I mean, that's why I.
No. Ignore that. If I did say quotient, just ignore that. So this is how you get the number of spanning trees which contain a particular edge. If you want it to contain E1, E2, EK, you have to merge all those edges. You have to merge all those edges and then do the counting. Okay. And if you want to count how many spanning trees do not contain 1 to 2, what will you do? It's not supposed to contain 1 to 2. What will you do? You just should delete that edge and get a new graph. If you delete that edge, you get a new graph and you count the spanning trees in the new graph. That's what will give you the number of spanning trees that do not contain 1 to 2. And so on. So what I gave you, the matrix tree theorem, the point, I am not expecting that you understood all of the things I said here. What I'm saying is that matrix tree theorem is a very basic counting problem. It extends to weighted graphs, including, of course, multiple edge graphs. and it extends to further refined counting problems where you are not just counting the total number, but counting trees which satisfy some properties, like you contain this edge, this edge, this edge, but not that edge. You can do all such counting using some determinant calculations. Okay. Any questions, comments so far? Okay. If not, I will close this topic here. I will just give you a preview of what I will do next time. Okay. Yeah, just a preview of what will come next time. Which is tomorrow. So we have seen, so let's take a finite graph as always, G is VE, and so L is the Laplacian. We'll write it as lambda 1 F1 transpose plus so as I said, lambda 1 is 0, F1 is the constant vector divided by square root n, and lambda 2 is the next eigenvalue, and so on. Right? This is the spectral decomposition. So we have seen lambda 2 is 0 if and only if G is disconnected. Okay, so that is G is connected if and only if lambda 2 is strictly positive. Now, in many graphs, it is not really disconnected. Okay, so when is disconnection important? So maybe let's say you have a class of students, and there are two groups where they don't talk to each other. Okay, so let's say a friendship graph in a class. Okay, so there are a bunch of students who are, so for some reason, maybe politics, maybe something else, they have formed groups. Okay, so there are here also, it's not like in the two groups everyone is friends with everyone else. So maybe there are friends, but somehow there is a division in the class. Nobody in this part of the class talks to the others in the class. So this is one set of people and this is one set of people. For some reason, there is nothing common between them. So their friendship is only between this group and between this group. Okay, so that is disconnection. But in real world, it can be not necessarily classroom, of course, Facebook or somewhere else. What happens is maybe along political lines or along some other lines, there is disconnection. People don't talk to each other. But of course, it's not absolute, right? I mean, maybe there will be some. So it may be true that it may be true in a general sense, but maybe there is just, for some reason, maybe they are neighbors or something. So some two friends are there. Okay, now the graph is no longer disconnected, right? I cannot say anymore that this is disconnected. Nevertheless, in some sense, it is weakly connected, right? It is true that there is some large group here which is well connected. There is one group which is well connected here, and one group which is well connected here, but the connection between them is sort of weak. It is still true that it is a weak disconnection. How do we make sense of weak disconnection, and does it have anything to do with lambda 2? That is the question that we want to address. So how to make or I should say weak connection, right? Weak connection. In some sense, it's connected, but weakly connected. So I should not say weak disconnection, it is weak connection. Okay, so how to define weak connection, and what does it have to do with lambda 2? In other words, if lambda 2 is exactly 0, we have disconnection. What if lambda 2 is extremely small? Does that mean that there is a weak connection? This is a very important thing, and we will study this point. So the key word, if anybody wants to look up anything on it, we will talk about what is called Cheeger's inequality. So really there are two inequalities we will talk about. It's the Cheeger-Boozer inequality. This is something from geometry, but it can be done in the level of graphs. It was noticed earlier, and it is very important for many things in probability and combinatorics. Okay, so we will talk about how to define weak connection and then how to capture it in terms of lambda 2. I hope I will be able to prove most of it, but maybe not, maybe we'll see. Okay, I will stop here.
Thank you